Hello, our project Path Planning with Deep Neural Networks was a collaboration between the Computer Science and Engineering and Electrical and Computer Engineering departments. Our sponsor is Mitsubishi Electric Research Laboratories, or MERL. Here are the members of our team with 3 ECE students on the left and 3 CSE students to the right. The overall goal of this project was to create a path planning system for a car, making it semi-autonomous by transforming sensor data into reference trajectories that a car follows using a motion planner. Our project has some specific tasks associated with it, including setting up a miniature scale testbed vehicle with sensors to perceive the environment, generating a training dataset for a vehicle maneuvering on the road, and developing and test a deep neural network that uses the sensor data to determine a reference trajectory for the vehicle's motion control system. These tasks are split between the ECE and CSE members of the team. Merle wanted this system developed to display the viability of a deep learning model for the vehicle control, as it takes less time and computational resources than traditional methods, which require the construction of dynamic maps of the environment. The CSC members of the team were able to create a control system for a car that's composed of a neural network that takes an image of what is in front of the vehicle and outputs a reference trajectory to be followed, a PID controller for regulating the speed of the car, and a pure pursuit controller for determining the steering angle the car should take to follow the reference trajectory by the neural network. These three components were implemented in Python with the neural network using the TensorFlow library. We were able to use the UConn's high-performance computing facility's GPU nodes to speed up the training process. While electrical engineering members of the team were designing and building the testbed, we used the Carla driving simulator, which has multiple maps in an autopilot mode to collect training data and validate our control system. For this project, we trained multiple neural networks, including encoder-decoder networks and multiple recurrent convolution architecture variants. The architecture that worked the best was a modification of a model produced by NVIDIA called PilotNet, and it is shown on the left side. We modified the architecture by adding recurrent layers, which enable us to pass time series data, in our case consecutive images from the camera, to obtain an output based on more information than one image could provide. In order to artificially expand our data set and increase generalizability, random image augmentations were applied to each batch during training. The training process was successful, achieving a minimum validation mean squared error loss of just 0.004. As you just saw, the neural network fit to the data well. And here's an example of how it runs in the simulator. We can run the simulator with commands from the network and controllers to visualize what this looks like. Shown here, the car maintains control within the lanes and can follow the curve of the road, starting out straight, turning, then returning to straight.
The image on the right shows the car in its complete state. We have implemented a camera that captures the 30 FPS video, a LiDAR that calculates the distance from objects to the car, an IMU that provides the motion of the car, and encoders that provide the speed of the car. We focused on low-cost sensors and easy configuration. As asked by our sponsor, we used Robot Operating System, which has a collection of open-source software libraries that allowed us to establish a communication between the Arduino, Raspberry Pi, and laptop.
Our design approach focused on using open source or commonly available parts that would allow for easy reconfiguration and long lifespan. All of our drive components were based on off-the-shelf RC components. That makes the power systems easy to replace and reconfigure as desired. Our computing systems were based on Arduinos and Raspberry Pis. Which are open source products with large software bases that would allow for easy incorporation of other sensors in the future. Our hardware focus used a laptop, and a Wi-Fi connected laptop with a superior processing power, or to implement the neural network.
Here we can see a video of the car driving around one of our training courses, with fake lanes for the car to stay within. On the bottom of the screen, you can see the camera and data output from the Raspberry Pi sent to the laptop using Robot Operating System. This is an example of recording training data as the car is being controlled by an Xbox controller, and the data from the Raspberry Pi is being saved to the laptop. In summary, next slide. In summary, we were able to successfully train a neural network using the Carla simulation software. We were also able to build a testbed that uses Robot Operating System with a varied set of sensors to drive like a road vehicle. Moving forward, we will continue taking training data so we can retrain the PilotNet model to work with our robot. We also wanted to say thank you both to our advisors at UConn and our sponsor, Mitsubishi Electric Research Laboratories.